Sampling distributions is what we're going to be looking at in Chapter 11. Now, just to review, we have our population. That's everybody that we're trying to study. Any number that describes something about that population is referred to as a parameter. We also have a sample, which is a small subgroup of that population that we actually collect the data on. Any number that's describing something from that sample is referred to as a statistic. And remember, we're trying to study this sample so that then we can make conclusions about the whole population. Also, to refresh your memory, that mu represents the mean of the population. However, x bar represents the mean of our sample. Also, keep in mind that sigma, the O with the tail on it, is your standard deviation of your population, and S is your standard deviation of your sample. The law of large numbers. You can have a random phenomenon occurring, but as you continue to increase the number of observations you do, that average ends up leveling out at our average of the population. So as we consider the law of large numbers applet, let's go ahead and roll our dice, and I'm going to say we roll it for 40 times. If we roll our dice, it's going to vary a lot to begin with, but it should eventually go ahead and start leveling out at our actual average that it should, and that it should end up being at 3.5. You might be wondering, why is it 3.5? Well, if you small number on a dice is 1, largest number is 6, you add them together, you get 7, divide by 2 to get the middle, and that's 3.5. And as you continue to go ahead and roll your dice, you'll see that yes, it varies a little bit, but it's going to continue to eventually get closer and closer to 3.5. Casinos, once again, use this idea of law of large numbers to work in their favor. Also, insurance companies do that. If you only insure a couple of people, you could really lose a lot of money, or you could still make money. But if you insure a lot of people, the law of large numbers guarantees that the insurance company will not end up losing money. So, what happens if we take multiple samples of the same population, calculate the mean, and make a histogram of all those means? What would the shape of that histogram be made from all those different samples? Well, that ends up giving us a sampling distribution. Your sampling distribution is, once again, when you take a sample of a certain size, we'll just say of size 10, and you take a sample of size 10, collect your mean from that, take another sample from your population of size 10 using simple random samples, and you plot all your means, you end up getting a sampling distribution. Now, keep in mind that the law of large numbers tells us that our sample, as we continue to increase the size, the average should end up getting closer and closer to our theoretical, or the population. But that's not what our sampling distribution is talking about. It's talking about what happens when you take repeated samples, and what's that average end up being. Your sampling distribution, which is a sampling distribution of x bar, your sample means, if your original population has a mean of mu and a standard deviation of sigma, your sampling distribution is going to end up being smaller or narrower than it would be if it was just your whole population of individuals. Here we're taking a sample size of 10, and since you're selecting a different sample of 10 people each time, you get a slightly different mean because each group of 10 people is different. But all these means, if you plot these, should end up giving you a shape of a normal distribution. The middle of this normal distribution should match your population mean. So, what's going on with your sampling distribution? Your sampling distribution, the mean of your sampling distribution should match the mean of your population. Your sampling distribution, because you're dealing with samples and you're looking at the averages of those samples, is not going to vary as much. So the standard deviation of your sampling distribution is your sigma from your population standard distribution divided by the square root of n. So basically, what happens compared to your population is you're not spread out nearly as much, and if you're not spread out as much, you're taller in the center. When we're saying that our average of our averages should match up with our population mean, we're saying that that should be an unbiased estimate, meaning on average it should be correct. But your standard deviation, because you're dealing with samples and samples don't vary as much, and since they don't vary as much, it ends up being your sigma over the square root of n for your standard deviation of your sampling distribution. So consider this. This is your whole population taking on all the values from around 45 down to 5. It's fairly spread out, and remember your whole area underneath this population 1 would have to end up being 1. But if you're looking at samples from that same population, you're going to still have the same mean right here in the middle at 25. But because you're dealing with samples, it's not going to be spread out as much, so it's going to be much narrower. And if you're not as wide, to still get an area of 1, it has to be taller. So your population mean may have a normal distribution of size, or normal distribution with a mean of mu, standard deviation of sigma, but your sampling distribution will have the same shape of a normal distribution, same mean, but because it's based on samples, your sampling distribution will have a standard deviation of being sigma over the square root of n. So, suppose we have a large population. We know the mean is 112 and standard deviation is 20. Suppose we took 200 adults randomly and we built a sampling distribution. What would you expect your mean and your standard deviation to be? Well, you're going to expect it to be approximately normal. Your mean up here was 112. That's going to match the mean of your sampling distribution, and they all had that. Your standard deviation, though, is going to be a 1.414. How do we get that? Well, remember that it's sigma over the square root of n when you're dealing with a sample. So you're going to take your sigma, which is 20, divided by the square root of n. N is your sample size of 200. And 20 divided by the square root of 200 is 1.414. So let's consider these two situations. We want to know what's the chance of you being misdiagnosed after one sample. Being misdiagnosed means you'd want to be having something smaller than a 3.5. Well, that's just our normal distribution, or z-score stuff that we looked at in Chapter 3. You go 3.5 minus your mean of a 3.8 over your standard deviation of a 0.2, and you get a z-score being negative 1/2. With a z-score being negative 1.5, negative 1.5 in the middle tells you your proportion, which is a 0.668. And so that's how we got this value here, which if you move your decimal point over, it's almost 7% of the time a patient will be misdiagnosed with one sample. But let's go ahead and consider the situation. Instead of doing one sample, we do a sample on 4 separate days. And so we have a sample size of 4. Let's go ahead and figure that out. We want to be less than a 3.5 to be misdiagnosed. Minus your mean of a 3.8. Since we're dealing with a sample, we got to put it over the square root of n for your standard deviation. So you go your standard deviation of 0.2 divided by the square root of 4 because your sample size was 4. When we work this out, we get a z-score being a negative 3. A z-score of negative 3, when you look at your chart, is this right here. And that's where we got this value here. If you change it into a percent, it's like 1/10 of a percent. So we get a much more accurate result or chance of misdiagnosis if we go ahead and look at a sample size of 4, which really isn't all that big. So why don't we always take multiple samples to get a more accurate result? Well, it's not necessarily always practical. Sometimes no more than a handful of repetitions is acceptable when you're dealing with samples from human beings. Also, there's more cost involved, and a large sample is not always attainable. Let's take a look at your central limit theorem. The central limit theorem says that if you take a large enough sample, that your sampling distribution will end up being normal. Now, your original population may be skewed, and that's okay. But the central limit theorem says if your sample size is large enough, your sampling distribution ends up being normal. So as we look here, here's your population, definitely skewed to the right. But if you just take a sample size even of 2, yes, it's skewed, but not nearly as much. Sample size of 10, really not all that big. It's starting to look normal. Slightly skewed to the right, but not bad. Sample size of 25, it sure looks normal to me, even though our original population was skewed. So let's consider this situation here. We have two situations where we have 1,000 simple random samples of either groups of 100 incomes or of 25 incomes, and then we plot these. Which one would be which? Well, remember that if you have a sample, which we're dealing with, your standard deviation is always over the square root of n. And if we put it over the square root of n, putting the larger number on the bottom is meaning we're going to get a smaller number out. So a larger sample size means we're not going to vary nearly as much, so that would be the one on the right. A smaller sample size of 25 would be this one here. Yes, it's still somewhat skewed, but a lot more normal looking than it was before, and not nearly as spread out as the other one. Even though your original population is, or not population, histogram would be strongly skewed to the right since you're dealing with income. So let's take a look at your central limit theorem. Here, as I increase the sample size, here your original population is strongly skewed to the right. As we increase our sample size, you can see that it becomes closer and closer to normal. Even a sample size of 50, it's hard to distinguish the difference between our normal distribution and the not normal. So, how large a sample size do you really need for it to be considered normal? Well, a sample size of 25 is generally large enough to be considered normal, even if there's strong skewedness. A sample size of 40 is enough to make it normal, even if there is extreme skewedness and outliers. And typically a sample size of 25 is really not all that big.